we have section 7.6 exponential functions. Sorry if the mic was bumping around for those listening. So an exponential function. This is the equation of an exponential function. So up in that top, we should have written down under exponential function in the first part of the notes, y equals a b to the x. Now, here's an example, everybody. You may want to write in that same top section. If we had y equals 100, now that's going to represent a, times 1.12 to the x. That's an example of an exponential equation. Now the exponent, as you write this, if you're watching at home, you may need to pause this, but the exponent is x. It's the number up in the air. We just got done dealing with exponents. X to the 7th. 7 is the exponent. We just did a whole bunch of stuff with exponents. But in this case, x is the exponent. Then a is the initial or the starting value or the y-intercept of the graph. So what that would mean is, if I said, what did we start with? We started with 100. So an example could be we start with $100 and we invest it in some stock, okay? Then B is this number, and it's the growth or the decay factor, and we'll talk about that. And it's pretty easy. If you look at this, this number is bigger than 1. So anything bigger than 1 grows. Anything smaller than 1 would decay. It would get smaller. And we'll talk about that as we go. But this one would grow by actually 12% every time we put in a different value of x. Okay, in the next part, as we graph exponential functions, again, it's in the form y equals ab to the x, which you see on your, well, it doesn't have it on your paper, so you may want to write that. And where a can't be 0, so you're going to want to write this down in that section, the second section. A can't be 0. When you see an equal sign with a line through it, that means a is not equal to 0. So in other words, I can't start with nothing and expect it to grow or shrink. Okay, you can't. You have to start with something. So you can't have exponential growth if you have nothing to begin with. So when we look at this value, going back to here, if I had put a 0 here, 0 times anything 0, I wouldn't have anything. A can't be 0, and that's what's written on this slide of the notes. B has to be bigger than 0, and B can't be 1. You don't have growth or decay if it's 1. If it's 1, if I multiply by 1, it stays the same. So now we see something here, like this one says y equals 2 to the x. This graph of this red line on this part, which is on your notes, y equals 2 to the x, it's growing, it's doubling all the time. This one, y equals negative 2, negatives end up going down. Okay. This one says y equals 1/2 to the x. Everything gets half the size, so everything shrinks. And this one's negative 1/2 to the x. Now, one thing you should see is you should see like this line here, or y equals x. These two are the mirror image of each other. They are what we call a reflection of each other. Okay? So, tables. You're going to want to put a couple tables in this section. And this one is a table going across. And as I'm looking at it, so we're going to make a quick table. You're just going to make a table like you see here. You're just going to go x, y, and you're going to fill some things in. So I'm trying to help so you know what do I need to write here. Well, start by putting in for x, negative 1, then 0, then 1, then 2, like it appears on the first table. And now at negative 1, it says the y value is 1/2. Now we have to think, what happens? Here, the difference between these x values is 1. They're all going up by 1. And you're going to see that a lot in exponential functions. A lot of times when you graph the x values, those go up by 1. And what we're really going to look is what happens to y. And in this case, if I took 1/2 that is appearing here and I doubled it, 1/2 times 2 is 1. So this one is twice as big going from here to here. But then if I double it there, take it times 2, I get 2. If I take 2 times 2, I get 4. So what we notice is these are multiplying by 2. This would be the graph. Y equals 1 times 2 to the x. I've got it written here a little bit differently. I don't put the 1 there. Okay? This would be an exponential function because at 0, we have one item. That's the starting value. You can always look at your 0 and figure out what your y-intercept is or your initial amount, your starting value. And then it doubles all the time. Now, I've got another graph on here, so if you're putting under that tables, you may want to put this one vertically. So I don't know how you split it up going across there, but this one, notice again, the x values. If you copy this table, so I'm going to do it kind of with you, so those going along. If I start out, this is 1, this is 2, this is 3, this is 4. What are the values? At 1, it says it's 16. At 2, it says it's 4. Now, how would I have gotten there? I divided by 4 to get the next one. If I divide by 4 to get the next one, I get 1. If I divide by 4 to get the next one, I get 1/4. I know, you're copying it in that area that says tables of exponential functions. You're copying those tables. So that's why I said we copy this table. All I did is copy the same thing that is here. And now you copied this one. I'm just showing you, these are just examples of what a table looks like. Some of them go across, some of them go up and down. When you look at a table, you should be able to write the exponential function. So for instance, this one, I might have to back up and figure out, well, what was it at 0? If I go backwards, let's go backwards. If I divide by 4, what would you get if you go backwards to get to these? 1, to get to 4, you would have to multiply by 4. Multiply by 4. So what do you think this one would be if you have your calculator? 64. Because 16 times 4 would be 64. So this equation, if I wrote it, would be y equals 64, because that would be the starting amount. It's the amount at 0. We don't have it on there. Times 1/4 to the x. Okay, because each time to go to the next number, we divide by 4, divide by 4. Dividing by 4 is the same as multiplying by 1/4. Okay, next, in example 1a and example 1b, it says, does the rule represent an exponential function? Explain. Okay, so we're going to see. To be an exponential function, you have to be able to put it in this form. Y equals a times b to the x. So a is the starting value, or what you have when you have 0. Well, what I have when I have 0 is -1, so that would be my value for a. Now, if I look at these all go up 1. Always compare those. Now, what happens to y? To go from -1 to 3, what would I multiply by? Or -1 to -3? Well, if you multiply by negative, it would turn to positive, so I would just multiply by 3. Now, if I multiply by 3 again, do I get 9? If I multiply by 3 again, do I get -27? So, 3 is what I multiply by, and I raise it to the x. So, does it represent an exponential function? Yes. And the reason is, it is consistent and it always multiplies by 3. It's always times 3. And then I can write that. That would be the equation. Now, we usually don't put the -1 in there, so usually we turn it to -3 to the x. table represent an exponential function? Okay, so this one, first, let's look. These are going up 1, up 1, up 1. So that's what we generally are going to look for in the x. But this one, on the bottom, to get to that one, if I multiplied, I'd have to multiply by -1 to make it +1. Then if I multiply by -1, it doesn't work. What each of these are doing are going up by 2. Okay, if you add 2, if you multiply each time, it's called exponential. But if you add, that is what we call a linear function. This would form a line. It wouldn't form an exponential function. This one, if we graph it, it would end up doing this and have the exponential shape like those first graphs. It's the graph of a curve. This one would be the graph of a line. So in B, it's no. What you have to remember is if you add each time to get the next number or subtract each time, that's linear. Okay? Part C over there. You're like, where's part C? It's way over on the right. Is this rule an exponential function? It has to be in the form y equals a times b to the x. Well, a, if we look, a could be 3. But the x isn't up in the air. The x is down here on the bottom. So this one is an x squared. This would be the graph of what we call a quadratic or a parabola. So the answer to this one is no. It's not the correct form. You have to have something like this. Y equals 2 times 3 to the x. Bottom line, the x isn't up in the air. The 2 is. The next one, does that look like an exponential function? Yes or no? Y equals a times b to the x. Okay. Yes. And basically, as simple as we can make it, x is the exponent. Okay. Okay. So now, writing some exponential functions. An initial population of 20 rabbits triples every half year. The function is f of x. Now remember, f of x, when we were doing things on the calculator, it would always, when we had to add those different graphs, we'd say tab. It would always say f of x in there. So let's remember f of x is, again, just y. So this is really the equation y equals 20 times 3 to the x. So that's an exponential function. We recognize it. We got A and B. It gives the population in half-year periods. How many rabbits will there be in 3 years? So first of all, notice it starts with 20 rabbits. That's the starting. That's why they have the 20 there. It says it triples. Triples means times 3. That's why we have the 3 there. But x is a half-year period. After 3 years, how many half years would have gone by? 6. Good. So all we're going to do here is we're going to take our calculator and we're going to go 20 times 3 to the 6. Now, if you didn't get 6, understand, a half year plus a half year is a whole year. That's 1 year, right? And that's 1 year. If we do this, we're trying to get 3 years. How many times would we have to do it? We'd have to have 1, 2, 3, 4, 5, 6 half years. Do you get where the 6 is coming from? So that's why we're putting the 6 in. Now we're just taking our calculator and we're saying, how many rabbits would there be? 20 times 3 to the 6. 14,580 rabbits. Example 2b. There are 30 flower beetles. They're left undisturbed in a warehouse bin. The beetle population doubles each week. Okay, so they came up with this equation. We start with 30, and it doubles every week. Now, how many beetles will there be in 56 days? So we're not going to put 56 in there because 56 is in days. We have to come up with how many weeks have gone by. How many days in a week? So what do we do with the 56? We should get 8 weeks. So we're then going to put an 8 in here to figure out how many beetles we have. 30 times 2 to the 8 weeks. 7,608.